Okay, done. Thanks. Yeah, so MeerKAT stands for MeerKAT, which CAT was the Karoo Array telescope, which was a prototype even of MeerKAT, which is based in Carnarvon, and we have 64 13.5 meter dishes in an array with the maximum baseline of around 8 kilometers. And it's designed with most of the antennas packed very closely within 1 kilometer, and then just a few antennas on the outside. And I'll explain some of the science reasons for that particular design a little bit later in the talk. But yeah, it's been operating since 2018, and we have very, very sensitive receivers. It's one of the kind of impressive things about our telescope is that we managed to design these very sensitive receivers. And so we have excellent sensitivity. This is a picture from inside the core at the site in Carnarvon. And we have 3 different receivers. We operated UHF, L-band, and S-band. The UHF and L-band receivers were designed and manufactured locally by a company called EMSS in Stellenbosch, and they're responsible for this really excellent receiver sensitivity that we have. And the S-band system is being designed by Max Planck in Germany, and they're also installing those receivers for us at the moment. It's a combined joint project. Yeah, so as you can see, it's very impressive when you're out there, and the whole telescope is operated remotely from Cape Town. So our offices are just across the road here, in case you didn't know that. And the people who do the operating are based there, and they operate 24/7 because you can observe radio during the day as well. Yes.
Can all 3 receivers be used at the same time?
No.
Okay, so you hook them on a different receiver.
Yes, yeah, you can't use them at the same time. Some antennas have that feature, but we only use 1 digitizer, so you have to connect the digitizer to that particular feed. So there's not 3 separate digitizers, so you can't use them at the same time. I don't know why whenever I press this button, it doesn't want to do anything. I feel like it doesn't like me for some reason. Yeah.
It doesn't like me, sorry.
I don't know what else to try. Oh, okay, if I click on it. Okay,
Yeah, sorry, I probably close my system.
Yeah, so those are all the dishes, and then this is kind of the operation heart, really, of the telescope on site. And this very big building here is the dish construction shed. So this is where they constructed all the dishes on site. And this building here is where the underground data center is. So we have a purpose-built underground data center that has been completely RFI shielded to prevent any signals from electronic leaking out. So it's encased in a kind of mesh Faraday cage underground. And what you can't also see in this picture is that it's taken from a giant kind of earth berm, which is all the ground that was excavated to make this underground data center, which then creates further RFI shielding from that data center. Okay, now I'm going the wrong way. Okay, yes, finally. So I don't know if you've seen these pictures before, but this is from construction. This is one of the dishes coming out of the dish construction shed. Here it is on the back of a truck, and here it is being lifted onto the pedestal. And as you can see, this was a very impressive engineering undertaking, and it's really great that it went so well. But aside from the actual impressive engineering, we also did quite a lot of exciting things in software. And this is from inside the data center that I just showed you. And here are some numbers indicating the kinds of processing that we're doing on site. So here in the data center, we do all of our real-time calibration and averaging, and we also do all of our real-time imaging. And that uses around 100 teraflops of compute and 6 terabytes of RAM, and get our data at a rate of 200 gigabits per second from the correlator. Once we've finished averaging everything, then it gets transferred here to the CHPC, where it goes into a long-term archive. We have a special Ceph object store archive, which is on spinning disk with 20 petabytes, and the data lives there for 6 months. And then after that, it gets transferred to tape. And we have a large tape archive also in the CHPC. And that's basically just like a big fancy jukebox. And all the data lives there for the rest of its life. And it is available for scientists forever from then onwards. And we're currently in the process of building another tape archive on site to have a second backup copy of that. And it produces roughly 20 terabytes of visibilities for an 8-hour observation and about 12 terabytes of images. So very high data rates. And this was very impressive, especially when we first commissioned in 2018, although these numbers are not perhaps as impressive anymore. And then very soon, we're going to be delivering something called MeerKAT Plus or MeerKAT Extension, which is another 16 dishes that will be added to the MeerKAT array. And here you can see all the green dots are where the MeerKAT dishes are, and all the blue dots are where the planned MeerKAT Plus dishes will go. And they'll basically add on longer baselines to our array out to a distance of 16 kilometers. It's jointly funded by Max Planck of Germany and Zereo. And instead of using the MeerKAT design dishes for this, these will be the SKA design for the dishes. So we have 13.5 meter dishes, and the SKA will eventually have 15 meter dishes. Just a bit of a plug for us. If you are interested in going to see this, we're having an open day on the 5th of July. So normally the site isn't open to members of the public because we don't want people with their Bluetooth watches messing up our data. But if you would like to go, it is open then, and here you can find out more here. I think it's around 350 Rand to go on the open day, but obviously you have to schlep all the way up to Carnarvon yourself. So yeah. Unless you're like the minister, people don't normally get to go to site. So yeah, as I mentioned, the precursor array for the SKA. So the square kilometer array was this idea that was conceived to have a square kilometer collecting area. But in reality, I mean, it probably won't be as much as that in the end. All of our ambitions have to be scaled back when the budget comes in, as I'm sure you know. But it's basically going to be 2 telescopes. One is called SKA Low, that's going to be sited in Western Australia. And it's called Low because it's going to be doing the low frequency part of the radio spectrum. And it's going to have 100,000 antennas spread over 512 stations, where a station is this little collection of antennas all together. So they kind of correlate all the signals from the stations into one signal, and then they correlate the 512 stations separately afterwards. It has a maximum baseline of 74 kilometers, and it's going to have a data transfer rate of 7.2 terabits per second compared to our 200 gigabits per second, which looks a bit puny now, sadly. It's going to have these kind of very strange looking antennas. I've got a close-up here of what they look like. So these low antennas, they're not steerable like a dish would be. They're just fixed, and then you electronically steer them by the way you correlate the signals effectively. So they don't actually move, they're just fixed on the ground, and they have this strange Christmas tree design, and that's to allow the different frequencies to be detected by the different lengths of dipole on the antenna here. But the one that's of obviously of more interest to all of us is the FKA Mid, which is going to do the mid frequencies, and it's also going to be sited in Carnarvon, and is going to be co-located with MeerKAT. Will be 197 dishes in total, but that includes our 64 dishes. Our 64 dishes will be absorbed into that array. And we'll have obviously much longer baselines, 150 kilometers instead of 16, and a data rate of 8.8 terabits. And this is a picture of the prototype FKA 15-meter dish on site, the only one that's sitting there right now. And I know to the naked eye it looks very similar to the other dishes, but yeah, it's basically, it is actually slightly different. Yeah, and so we're hoping that this will all be up and running in 2028. And we're entering a very interesting time because we're going to be constructing all of these dishes on site, but we're still operating MeerKAT right now. And I don't think it's ever been attempted before to have such an active construction site on the site of an observatory. So we'll see how all of that goes. We have to have very strict rules about everything that goes on site. The SKA is a global organization. So obviously we have the 2 sites up in Australia. These are all the other member countries that are signed up. So if you want to be part of the SKA, you have to pony up some money. Don't get to be a member for free. And the headquarters are sited in Jodrell Bank. So they like to say 2 telescopes, 3 sites. You know, that's the jargon. Yeah. So that's basically MeerKAT and the SKA. Are there any questions about it at this point? How am I doing for time? I kind of tend to wrap it on. Okay. Yeah, so then we'll just carry on to talk a little bit about observing in the radio. So maybe you guys already know this if you're already interested in astronomy, but you know, the only real wavelengths that you can see from the ground that the atmosphere can penetrate through the atmosphere is visible light, which is why we can see with our eyes, basically, and radio waves. And pretty much all the other wavelengths get cut out by the atmosphere, and you mostly do them either from space or from balloons in the upper atmosphere. So, yeah. So the thing about observing in the radio is that, all right, if I skipped a slide, I feel like I did. No? Yeah, but anyway, the thing about the observing in the radio, as I'm sure you're also aware, is that obviously here you're looking at 700 nanometers or so in the visible light, but here you're talking about tens of centimeters or even tens of meters. So radio waves are very much longer than visible light waves are. And that presents some interesting challenges when you design your instrument. So again, as you probably know, if you're interested in astronomy, is that you have resolution of your instrument. So if you make your aperture bigger, then you can see finer and finer detail. And there's this famous equation called the Rayleigh criteria, which says your resolution is equal to the wavelength divided by the aperture size. And so if you make your aperture size bigger, then you can see finer and finer detail. And if you make it smaller, then sources will become blended together and you'll see less and less detail. And you can think of resolution also kind of like pixel size. So if you have very big pixel sizes, all the details get blurred together. And if you have small pixel sizes, you can see things with more clarity and more sharpness. So of course, the challenge here is that our wavelengths are very much longer. And so that means that your resolution is just, because of this equation, going to be much worse in the radio. And so if we were to look at, say, and like the typical resolution of very famous optical telescopes like HST and JWST in the near infrared, they have 0.1 arc-second resolution with these size mirrors and the size wavelength. And if you wanted to get comparable resolution in the radio at 20 centimeters, which is a very popular observing wavelength and what we observe at MeerKAT and L-band, you need a dish that was 50 kilometers in size. Well, that's, I mean, obviously hugely impractical. And even the largest steerable dishes are only about 100 meters in size. So that's, suspending an enormous rugby field above your head on some kind of mount, and it's made of steel. A very impressive engineering feat. This is one of the biggest telescopes in the world, the Green Bank telescope, and it weighs 8.5 tons. So it clearly becomes very practical to just keep expanding the size of the steerable dish. You can go to solutions like Arecibo, which is where it's not a steerable dish, it's just a dish built on the ground, and you steer it by moving the subreflector. This is a 300-meter non-steerable dish, which was very famous, and it was featured once in a James Bond movie long ago, for those of us who are old enough to remember that. But as you know, I'm sure many of you have seen that it suffered, catastrophic failure when one of these cables, supporting cables, snapped, and this whole subreflector crashed into the surface and destroyed it in 2020. So it's also just another illustration of, how difficult it is to keep making these things bigger and bigger. So what do we do? What choice do we have? Well, luckily we have this very nice cheat where you can connect 2 antennas together, and then you can get a cheat on that, and you can get the same resolution as you would have if the dish was the size of the separation between the 2 antennas. So you can build 2 antennas and put them like 10, 50 kilometers apart, and then you get the 0.1 arcsecond resolution that you would have with HFT. Of course, the downside is that nothing is ever really for free, and the difficulty of doing this is that it's more complex, so you don't get a direct image, you get a mathematically related quantity to an image. It tends not to be sensitive to all spatial scales. I'll try and explain that a bit more in a minute. And if you have very empty arrays, like you just have these 2 telescopes, you don't have a lot of sensitivity. So you can see very compact things, but you can't see very faint compact things, only very bright things. And then this is just to try and illustrate some of the features of this array style of observing. And I'm mostly trying to illustrate a point that I'll discuss later about why our design is useful. So number one, if you put your antennas on the ground like this, then you measure something called the UV plane, which is the separation vector between each of these antennas in projection from the sky. And if you just measure that, then you get these little measurements in the UV plane, and then you have to do something called the Fourier transform to get your sensitivity pattern on the sky. And if you do that, your sensitivity pattern doesn't look that great. It has all these weird ripples, it looks a bit odd. And if you take this pattern and you measure this image, what you get out from your array is this thing. So you have quite poor image quality if you just have these few antennas and you observe for a short amount of time. Luckily, if you observe for a longer amount of time, then the projected vector rotates as the Earth rotates. And so you can get better sampling in this plane, and you get a better kind of imaging function here, which gives you better image quality. So people call this aperture synthesis or Earth rotation synthesis. So observing for longer already buys you a lot better image, which is convenient because it would be way more of a pain to try and put antennas in all these locations, right? So this is a very nice feature. What you also might have noticed if you looked at that other image is that in this image here, unfortunately, I don't think it's showing up that well for you guys, but there's a little tiny point in the middle and these 2 lobes. This is what an AGN looks like. But in the picture, you're only really seeing this little tiny point, right? And that's because here there's a hole. If you put all your antennas far away and there's not much sampling in the very kind of closely packed space, then you aren't sensitive to very big spatial scales. So all this very big scale emission just gets filtered out. So you only see the very compact stuff. And if you pack all your antennas closely together, like in this case, and you sample in the very closely spaced space, then you're only really sensitive to the big emission. So this is what your image would look like if you packed all your antennas close together. This is what your image would look like if you pack all your antennas far away from each other. And so ideally, obviously, you want some kind of combination of this, right? So you try to design to have a bit of everything so that if you have some close antennas and some far antennas, then ideally you get this case where you've sampled most of the spatial scales and you get a nice reproduction of the sky. But it's never possible to do everything perfectly. So when you're designing your array, it kind of depends on what type of image you're interested in looking at, right? If you want to look at very compact, very bright, very far away sources, then you probably really want long baselines. If you want to look at very fluffy, close by things, you want lots of short baselines. And whenever you get a bunch of scientists in a room, that everybody fights like cats and dogs to get what they want, and nobody ever gets exactly what they want, right? It's an imperfect problem. So let's move on to radio emission from galaxies. So again, maybe you're already familiar with this idea, but if you look at the sky with a radio telescope, what you're typically seeing is not starlight. And when we look with our eyes, most of the things you see are stars. But if you look at a typical black body and a temperature that is consistent with most of our stars, then if you look down here, radio is way, way, way down here. And basically, there's just not a lot of emission from stars in the radio. And in fact, when radio telescopes, communications are being developed, people were saying, oh, it's not really worth looking at the sky with these telescopes or communication devices because there won't be anything to see. The sky will basically be empty. So of course, that's the thing, nature of science, you predict things and then it turns out you're terribly wrong and we just carry on. So as it turns out, we were terribly wrong, but it's true that there's not a lot of starlight. So what do you actually see? Well, you get two kinds of signal. You get broadband signals or continuum, so that's emission at all wavelengths. And the main things you get are, I'll explain it a bit more in detail, but you get free emission from ionized regions around hot young stars, from H2 regions. And then you mostly get this non-thermal synchrotron emission, which again, I'll explain, but it's to do with relativistic electrons that are interacting with magnetic fields. So you're getting emission from young stars, you get emission from supernova remnants, and you also get a lot of diffuse emission that's associated with things that have been generated in those supernova remnants. So that's what you get in continuum, and in spectral you get H1 emission. So that's H1 is neutral hydrogen when it's in its atomic form, which is the most abundant element in the universe. And this is a great way to probe the neutral gas content of galaxies effectively. So yeah, so free emission from H2 region, it's called free or Bremsstrahlung, is when you have electrostatic interactions between charged particles. So, radiation is usually generated by an accelerating charged particle. So you need something to generate the acceleration. And in this case, the acceleration is generated by this electron being flung around the proton. So the ionized material here is really created by hot young stars that produce enough blue light to strip the electron from the neutral atom and to create this ionization bubble around the hot stars. And this type of emission is normally thermal, so it depends very much on the temperature of the gas that's being emitted. Whereas synchrotron emission is when you have a relativistic electron, so it's moving at close to speed of light, interacting with a magnetic field where it spirals around this magnetic field and emits radiation. So really what you need is obviously electrons, but you also need something to accelerate them to these near relativistic speeds. And this type of emission is not really thermal. It's not really related to the temperature of the gas at all. It's probing more things like the magnetic field of the system. So yeah, I think you all know what supernova explosions are. So when they explode, they accelerate these electrons as many of those heavy elements are being made and electrons are being kind of produced during the explosion. So they are actually inside the supernova remnants. This is the supernova remnant, observed with MeerKAT. And this shell here is all synchrotron emission generated by these relativistic electrons. But once the initial explosion has happened, many of these electrons will continue to travel outside the supernova remnant and retain that near relativistic speed, and they'll interact on a lower level with the global magnetic field of the galaxy, and so that creates diffuse radio emission in the galaxy as well. Then for the H1 case, you get the spin flip transition where when the one electron changes its spin state to be anti-aligned with the proton, then you get a small amount of emission. This is a very rare transition, but because there's so much H1, you can still see it in galaxies. And as you know, spectral lines are just confined to a small frequency range, which makes it harder to see them really to very far distances, because with continuum, you can add up all your signal over a big frequency range to get a bit of a sensitivity boost, but you can't really do that with spectral line. But the upside of spectral lines is you know exactly what frequency they're meant to be at, and so any shift from that frequency is due to the motion of the gas that's emitting, and so you can use that Doppler shift to probe things about the dynamics of the system. And normal spiral galaxies emit these H1 spectral lines in this double horned profile, where one side of the spiral will be rotating away from you and the other side will be rotating towards you. Yeah, so this is just an example of what H1 emission looks like. This is here where it's color-coded by its velocity, where the red is receding and the blue is moving away from you. This is what it looks like in total intensity. Here it is, the purple is the H1 and the yellow is the optical light. And the nice thing about H1, or the interesting thing about it, is that it usually extends much further than the optical light. So you can really probe the dynamics of the galaxy well beyond the light that you can see with the stars. And it also allows you to probe other interesting dynamics like tidal stripping of the gas, or even interactions between galaxies. For example, here, this is the optical picture. I mean, these things look like they're not really doing much. You wouldn't have guessed they were interacting. But in the H1, you can see clearly that there's quite a lot of interaction going on between them. So it's very good at probing this low density environment. But the difficulty is that it's quite hard to see it far away. It gets faint very quickly. And this is a H1 image made with MeerKAT of M83. So you might say, okay, well, that's great. Like, I can see that you can study galaxies with radio, but like, why would I? I mean, I have my awesome HFT telescope. Like, why would I faff around with this radio thing? It sounds complicated. So why do you want to do with radio? Well, basically, radio has this nice property that because the wavelengths are long, it can penetrate dust clouds. So dust grains usually absorb UV light because they're in between you and them. But because they're quite small, these dust grains, they don't absorb radio wavelengths. And when these dust grains absorb UV light, they tend to then re-emit in the infrared. And so a lot of starlight in UV and optical surveys is actually missing. Can't see it, you just have to assume some kind of dust correction to work out exactly what your star formation rate is. And this is a nice illustration of this, where this is the Sombrero galaxy in the visible, and you can see these very dark lanes here. That's all dust obscuration in the visible. And here it is all lit up very nicely in the infrared, in the red color here. So you can say, okay, fine, but I mean, it sounds like far infrared can do a good job as well of looking at dust obscured star formation. And that is very true, but as we mentioned right at the start, far infrared is only really visible from space. And it's a longer wavelength as well compared to near infrared. And you're going to have to observe it with an instrument that you can pack onto a satellite. So this is the far infrared satellite, which is kind of the most recent state-of-the-art far infrared survey, and it has around 30 arc-second resolution. So you can only do it from space, and limited resolution becomes problematic because, as you can imagine, when you're observing deeper and deeper, the sky gets fuller and fuller, and now you have quite a big beam. And that beam is going to start blending together all the sources that are close to each other. And so what that means is that your image becomes confusion limited. So even if you observe for longer or with more sensitivity, you can't really see any more detail because all the sources have just been mushed into the one pixel that you have. And so because we can do radio from the ground and we have this interferometry system, we're able to overcome this limitation. So far infrared is a great way to probe dust obscured star formation, but it's kind of limited in how deep you can really see. And with instruments like MeerKAT and eventually the SKA, we'll be able to see out to much, much deeper distances, much further into the past, and won't have to do dust corrections. So we can actually directly detect, in some sense, the star formation. Although I have to add the caveat that you can't do a lot with just radio by itself. Radio is a great way to detect sources, but to get more information about sources like their distance and their properties and their star formation rates, you can do that a little bit from the radio, but you really do need complementary data sets or multi-wavelength astronomy, because synchrotron emission has very just has like a single slope spectrum. And so because of that, you can't tell a lot about the distance or luminosity of the source without this extra information. So it's a great way to detect things, but it does also have limitations. So what kind of work have we done already with MeerKAT? Well, with MeerKAT, during our commissioning time, one of our colleagues did this survey called the Deep2 survey. So when you're trying to image your sources, very bright sources in the field, I guess you can see it a bit like when your image gets saturated if you have a very bright source and you can't see the fainter things because the brighter thing is washing out the whole image. We have similar problems in the radio that if you have very bright sources, it can cause systematics in your images. So he selected this very quiet field in the sky so we could get away from this problem, and we observed it for 100 hours. Now, because we only have 8-kilometer baselines, we also don't have the best resolution with MeerKAT. We're about 6 or 7 arc seconds. So in this case, we're still very confusion limited. But this is this image with 100 hours. And using some fancy modeling and statistics, because we have to do that because we are confusion limited, we're actually able to measure with the radio emission what the star formation history of the universe looks like for a normal kind of Milky Way type galaxy after a redshift of 2. And this is this result here, which the radio is in the blue and the infrared and near infrared and UV is in the black. So they are sort of consistent, although ours implies that there's an even stronger decrease in star formation rate as you approach, late times or our time. But this is, the first time that you've actually been able to measure this kind of very ordinary low star forming galaxy out to this redshift, and it was done with MeerKAT. So that's very exciting. And then I also promised to talk to you guys about active galactic nuclei and black holes. So a black hole is a region whose gravitational field is so strong it prevents anything, including light, from escaping. So it has to have very compact mass, and an example of that, a black hole would contain the mass of the whole Earth in a single marble. And you can get stellar-sized black holes, but you can also get supermassive black holes, which are like 20 solar masses. So black holes kind of come in 2 phases. They can be just kind of sitting there, not really doing anything. And we believe that pretty much every galaxy in the universe hosts a supermassive black hole, but most of them are sitting around not doing a lot. And because you don't really observe any radiation coming from them, they're not really doing anything. How do you know they're there? Well, basically you can measure the orbits of nearby stars, and then you can use your knowledge of Newton's laws of gravity or general relativity to work out how much mass is contained and in what space. And you can see that there's definitely a supermassive black hole. So this is the one supermassive black hole in the center of our galaxy. And I think they've even managed to do this kind of proper motion study of stars in some of our neighboring nearby galaxies as well now. But then they can also come in a form where they're actively accreting matter. And when they're actively accreting matter, they are very bright, very energetic objects. They're accreting matter at a very fast rate. And as the matter kind of gets sucked into the supermassive black hole, it forms a superheated accretion disk, which then makes very bright emission. So they're the most luminous, most energetic objects in the universe, and you can see them, right out to the very ends of the visible universe. And they have a number of other interesting properties. So this is a kind of example of what a active galactic nuclei looks like. The idea is that you have a black hole in the middle, you have the accretion disk where the matter that's being sucked in gets sucked, flows along the accretion disk, which gets very hot and produces a lot of very bright radiation. And then you also have a number of these kind of different regions called the broad line and the narrow line regions. Anyway, those are just regions that are very highly ionized, and they have very interesting so what I'm looking for, velocity profile. They're moving very fast and they're also very, very highly ionized. And that's really how you can infer properties about your black hole, is from these different regions of gas. But when people first discovered active galactic nuclei, when they first discovered these very bright sources, they were kind of puzzled because sometimes you can see the very bright source, but sometimes you can only see these ionized bits of gas. And the way you can probe these ionized bits of gas is through their spectra. So in the end, they came up with this idea called the AGN unification model, where they say there's like a little dusty torus or donut. And depending on your viewing angle, you may or may not see the accretion disk directly. You might only see these dusty bits of ionized material, but that you believe that the accretion disk is still there. And some of these active galactic nuclei have very bright, very powerful radio jets, and some of them don't. So if they have the jets, they're called radio loud. If they don't have the jets, they're called radio quiet. Very complicated nomenclature system. So this is a sort of model of what active galactic nuclei look like. And some people argue that maybe there's a form of AGN that don't have accretion disks, but that's a little bit in dispute. But what is clear is sometimes you can see it visibly. So if you're looking at it face on, like down the jet here, you can definitely see it. But if you look at it from the side of this dusty torus, then you can't see it because the dust is absorbing all the UV light, right? Because I told you that dust, unfortunately, takes out your UV light. So what we're interested in studying, obviously, with MeerKAT are the AGNs that have radio jets. They're the ones that are most accessible to us. And the jets here are also synchrotron emission from a highly ionized plasma. So there must be magnetic fields here that are collimating these jets and helping to keep the material in that very long straight line. You can deduce interesting properties like how old the jets are by just considering things like their size. You know, they're not moving fast, the material can't be moving faster than light, so you can estimate roughly how old they are. You can also use things like their spectra to see how old they are. The questions that we still really want answers for, and that hopefully MeerKAT and the SKA will help us with, are things like, why are some radio loud and some radio quiet? Some people think that radioactivity is maybe triggered by a merger. Other people say it might be, dependent on the black hole spin. But really nobody actually knows. So what triggers radio AGN activity? How long does this activity typically last? Some AGNs show evidence of there being multiple lobes and multiple periods of activity. How common is that? And for example, is it the fact that in some cases you can see these multiple periods has something to do with how long they were active for and their duty cycle, or is it something else, something to do with the medium that they're in that's allowing the older jets to stay visible for longer? So that kind of thing. And another important question people want to answer is, do these radio jets play a role in regulating the star formation of their host galaxies and clusters? There are definitely images that show that these radio jets can push out material, and you can see evacuated holes in intercluster medium, but it's really not clear if that's an important effect. But as you know and saw, star formation in the universe is decreasing at late times, and people don't have a good explanation for why that is. And many people hope or say that they think it could be AGN activity, mainly because it's one of the most energetic phenomena. And if you need to stop star formation, especially in big galaxies, you need a lot of energy. But there's not a lot of direct evidence that this actually works. And we're hoping that with the better resolution that we're going to get with new instruments, you'll be able to see this more clearly. So these are just some, and then I forgot to say the most important thing. So if we go back to our original slide where I was talking about, packing how to design your array, whether you should have short baselines or long baselines, how do you choose and what's the best strategy? So the interesting thing about MeerKAT is that we chose to go with this design where we packed a lot of things into the central core, not really to do this type of science, not to look at AGN or to look at star-forming galaxies, because normally if you want to look at very distant things, you want that sharpness, you want that resolution. And so you would design to have more long baselines. So instead, the other more compelling science cases, which pushed us towards this tighter core design, were things like pulsar searches and pulsar timing, and looking at the H1 gas, which tends to be very diffuse in the nearby universe. So we kind of designed our array for that purpose. And many people were unhappy about that. They thought it wouldn't be so great for extra galactic AGN type science, this kind of thing, where this has been the bread and butter of radio astronomy since the beginning of its inception. Right? The very first thing that we ever saw with the radio telescope was this type of source, because they're so bright, so much brighter than an ordinary star-forming galaxy in radio, because like I said, the star-forming galaxies don't have a lot of emission from stars. So, but the really kind of interesting, and as one guy said, perverse thing about MeerKAT is that actually diffuse emission has turned out to be so much more interesting and so much more plentiful than any of us ever realized, because we were always designing our instruments with this bent towards having more resolution. We always had this idea that more resolution is better. And so now that we're doing a lot of surveys with MeerKAT, we're seeing a lot of really interesting features in the diffuse jet emission that have never, ever been seen before, and that we totally would have missed if we just done what we thought we should do from the start. So serendipity is a really interesting thing. And these are some of these kind of interesting features, which maybe don't look that interesting to you if you don't know what you're looking for. But for example, this one is a double lobe jet, but it has these little stripes. You can see like it's like little, I don't know, ratings on it. No one's ever seen that before, and nobody knows why it's doing that. And it's all because we've got this diffuse emission sensitivity. This is also what we call a bent tail radio galaxy. So it's like those other double lobe sources, but it's been bent. So that's the center, and these are the two lobes. But again, what's really interesting about this is that normally when it's bent like this, at the edges, it becomes very diffuse because it can't remain like that well collimated over long, long distances. And this one is not. It's very, very tightly collimated. So no one understands that either. And this is also another, a one-sided jet, but it's got all these strange spines here. Also never been seen before. And these kind of weird, like twisted features that nobody knows what they are either. This one is two radio jets in a cluster. So here, the central source with your radio jets, and then there's another one, that's the, unfortunately here, it's a bit saturated, so you can't really see, but there's another radio jet there. But again, what's really interesting are these filaments here that are lit up in synchrotron emission. So they're there, and there are also some filaments here connecting these two radio galaxies together. And people had seen something like this in much lower resolution images. So imagine the whole thing is really blurred out, and we're like, oh, I don't know what that is, and maybe it's just an artifact. But now with our instrument, you can see really clearly that's a real thing, and nobody knows what that is either. And now that we've seen them, we're seeing them everywhere. They're just popping up all over the place. So people think that there might be some magnetic flux tubes in the ICM that it's being lit up here. But I mean, these were never predicted. No one saw them before. None of our hydrodynamic simulations reproduced these, because nobody expected them. And now they're here. Now we have to come up with an explanation. And this is another really dramatic example of these filaments. It's another radio galaxy with these. So it's clearly not a, you know, it's a real thing. It's just, it's not an artifact. It's actually in there, but no one knows what they are. We've also got this interesting case of bent radio galaxies. So you do see these kinds of bent radio galaxies typically in very dense environments and clusters, but these galaxies are not in a cluster. Also very weird, and gives you this really interesting opportunity to use the bent shape here to try to probe the dynamics of the medium that they're moving in, because also they're not necessarily bent in the same way. So it's also a very interesting opportunity. And then this is my last example, which is an Xshaped radio galaxy. So, I mean, it's called an X-shaped radio galaxy because it's shaped like an X. People have known about these for a long time, and typically in less, lower resolution images where you don't have as much sensitivity to these diffuse jets, people haven't really been able to discern all the details of what's been going on. And so for a long time, people had two different theories about what formed X-shaped radio galaxies. One was that as the jet goes out, it hits into something, some kind of denser medium, and then the jet backflows. And then as it comes back, it hits into something else and creates this secondary lobe. And the other explanation was that maybe something happens to change the orientation of the jet, right? So that it was pointing one way and then it pointed another. And both these theories are considered equally valid. But in this image, you can really see there's lots of good evidence to support the idea that it's backflow. You can see that it looks like it's flowing back. And you can see that there's an overdensity here. This is where the galaxy gas is sitting. So there's a galaxy sitting right there, and it looks really clearly like it's flowing backwards. And if you zoom in here, these are two new jets. So these jets are old, and two new jets are forming, and they're clearly aligned with the original larger axis. So this is really like the strongest evidence that this backflow theory holds, at least for the source. I mean, you can't say whether it holds for all sources, but it's really, really interesting. And no one's ever been able to see that in this kind of detail before. And even more interestingly, I don't know how well it shows up for you guys, but you can see there's like this little fluffy bit on the edge here and on the edge here. This is a little cocoon. And they think that that might be a previous radio jet, but they don't actually really know. But that's the best theory that we have for the moment. And so anyway, these are the kinds of spectacular images that we're making with MeerKAT. And we have something like 39,000 of these multi-component sources in just our early data that we still need to look through. So these are just the ones we've managed to look at so far. And so hopefully we're going to do a lot of really interesting new science with AGN, with MeerKAT, and obviously eventually the FKA. Great. Thank you very much, guys. That's my
Thank you very much. For the interesting presentation. Are there any questions? And of course, if there are any questions online, please just unmute and fire.
I see some of the pictures are in different colors. Some are red, the jets. Some are red, some are purple.
it's all false color.
Is that false color?
It's all false color, yeah.
Now, the jets that are grown out. What is it? Is it hydrogen? Is it the whole?
Yeah, it's basically very ionized hydrogen.
Very ionized.
Yeah, it's ionized hydrogen.
It's created by the black hole or by the.
Yeah, the jets are driven by the black hole. Yeah.
So the black hole is making hydrogen.
No, it's not making it. It's just creating the conditions to drive that plasma outwards. It's not creating it from itself. It's just accelerating material that's already in the galaxy. Yeah.
Are the nuclei actually moving? Are they static or are they moving?
Yeah, they do. I mean, so, if the black hole is in the middle of the galaxy and the galaxy is moving, everything's moving together. They're not just sitting in one place. And I mean, obviously the universe is expanding too. So they're moving with the expansion of the universe as well. But if they're moving within, say, a cluster, which has got some, if you imagine like the galaxies are falling into the cluster underneath the gravity of the cluster, then they're all moving towards somewhere. I mean, they're moving slowly, right? We're not going to see movement in our lifetime, but they are moving.
For example, you've got a shape like that, you've got X-shape, AGNs. Do they change shape over a period of time? You've got magnetic interaction between magnetic forces and H1 clouds, whatever.
Yeah, exactly. So, exactly in that X-ray in this X-shaped one, that's what happened, right? The jets are coming out. So originally, when this thing first started, the jets would have been small, and then they've expanded and they've hit something, and then they're like, okay, now the material is being pushed back. And in theory, there's no real reason why. I mean, that's why people are saying, or maybe the black hole has changed direction. There's no reason why it couldn't, right? I mean, it would need some external force of momentum to change its direction, but it doesn't mean it can't move. It definitely can. So it's subject to the same gravity as everything else. But I mean, obviously, they're very gravitationally massive objects, so they have quite a lot of their own pull too. Yeah.
That was very interesting. Thank you very much. What is the difference between the 66-dish MeerKAT in resolution and the extra 16 dish? What's the difference in resolution?
It'll be about double. Double, yeah, because the resolution, remember, is related to the longest baseline, and currently we're at 8 kilometers, and when we've added these extra dishes, we're going to be at 16. So it'll be a double.
It's from what how many arc seconds to how many arc seconds?
Well, we're basically at 5 now, so like 2.5.
Oh,
But yeah, when we go to the SKA, it'll be a lot more because it's like 10 times, right? 150 kilometers. So then it'll be 0.2 on our second.
Last time when I was at the site, there was a Chinese company putting up a dish. Are they still putting up more dishes, or are they the ones that build this for other dishes?
Yeah, so the Chinese have the contract to build the SKA 15-meter dishes.
Okay.
So they're built, that dish that I said looks just like the MeerKAT dishes, that's the Chinese dish.
The Chinese one.
Yeah.
But they were basically putting it together.
Yeah, exactly. So that is the Chinese dish. That will be the dishes, well, the same design in theory for when the SKA happens. So they're meant to have 4 dishes on site by the end of next year for SKA, where they can actually start testing their software and doing real observation. Yeah, so there should be 3 more, but none of those 3 have landed yet anywhere on South African soil. So we're still waiting because they've still got to drive them there and put them up and so on. But they will also be assembled, I think, inside the same dish shed that our dishes were originally built in.
Just a question about the project like this, obviously very complex and so on. So for the new dishes, 15-meter dishes, how many companies are involved in putting it all together? There are too many components, mechanical.
Yeah, that's a good question. I mean, I don't have a lot of full insight into all of that, right? But I would say, for example, those dishes are being built or designed really by the Germans. So I would guess that several companies are involved there, right? Like you would need the people who actually are involved in making the dishes and the guys who make the receivers. Those are separate for sure. So that's at least 2. And then I think we would we do contract local people to do all the local infrastructure. So things like building the pads for the pedestals and putting in the fiber and all the digitizers. But okay, a lot of the work for those 20 dishes, we're reusing a lot of the same stuff that we did. Like the FKA, maybe I should have said, they've got different dishes, but they're also using a different back end. Whereas these new dishes for MeerKAT Plus, it's our back end, but their dish. So it's like a, sort of hybrid cannibalized thing at the moment. So I can't say exactly how many companies, but easily 10, right? I would guess.